Hey there, chemists. Welcome to another exciting organic chemistry lesson. Today's lesson should be short and has quite a bit of review in it as well of topics that we've already seen, as well as some introduction to some of our new organic molecules. So let's go ahead and dive right in. Today we're going to be talking about ethers, aldehydes, and ketones, three more of our organic molecules that we have not yet studied and that you can find right here in reference table R. So let's go ahead and take a look at our first two molecules that were provided here. So let's go ahead and compare these two molecules. How are they similar and how are they different from one another? So maybe take about 30 seconds or so, pause and brainstorm, see if you can come up with how they are similar and how they are different, and go ahead and hit that pause button now. And welcome back. And if you did pause, great. If you didn't pause because you weren't really sure, that's okay too. Let's go ahead and take a look. So something that may have immediately popped up for you as something that is going to be similar about these two molecules is that they both contain that double bonded O. This is a little bit thick of a pen. There we go. So they both have that double bonded O. Okay. Maybe you were able to recognize that they have the same molecular formula, right? They contain the same number of carbons, same number of hydrogens, and same number of oxygens. Now, what's different about these two molecules is the location of that double bonded O, or the structure of this molecule. So the structure or the location of that double bonded O. Okay. So these two molecules, which are going to be two of our molecules that we talk about today, either an ether, aldehyde, or a ketone, these two molecules are considered isomers of one another. And I know that when we reviewed isomers last, that this was actually kind of tricky for you guys, and so I wanted to continue to give you another example. So isomers, by definition, are going to be molecules with the same molecular formula, okay, but different structure, and therefore different properties. And again, as I mentioned in class when we discussed this, the more carbons, the more carbon atoms that are present, the more different isomers that you can create, the greater the number of isomers. Okay, perfect. So how do we distinguish these as either an ether, an aldehyde, or a ketone? I'm not going to give it away which ones they are, but how are we able to recognize? So when we are looking for identifying the class of the organic molecule, again, reference table R is going to be your best friend. So we have three different molecules here, and they all belong to either the ethers, aldehydes, or ketones. And what I want us to do is I want us to take a look at reference table R and determine, based on the functional group, which class of organic compounds these molecules belong to. So let's go ahead and box the functional group and predict the names of these molecules. So as we are looking here at our molecules, the first thing that we want to do is identify the functional group. So what I'm going to do is I'm going to, again, take a look at reference table R. And again, the functional group is usually going to be something that contains either double bonds or a different atom other than that carbon and that hydrogen. So for our first molecule here, notice how we have that double bonded O on the end carbon. And so as I'm looking through these molecules on table R, what I want to look for is a double bonded O, okay? And again, we're focusing specifically today on aldehydes, ketones, and ethers. So looking at an ether, that's going to be a single bonded O. That's not really what we're looking for here. And then we have aldehydes and ketones, and they both contain a double bonded O. So our functional group here for this molecule is located here. And this molecule is going to be considered an aldehyde. okay, an aldehyde. And in just a couple minutes, we'll talk a little bit about why it wasn't the ketone, and we'll talk about being able to distinguish the two very quickly and easily. But what I wanted to go ahead and point out here is that the general formula for this aldehyde, okay, is going to be R-CHO, okay, and that's our general formula. Now, how do I name this? Again, what I love about reference table R is that it does provide you with examples of how to name everything. So the example provided in the table was propanol. And as I'm looking at this, I'm recognizing that there's 3 carbons in my example, hence prop, and then the ending ANAL or anal, okay? And so as I'm looking at this molecule here, in order to name this, what I want to do is count my prefix or my number of carbons. So we have 1, 2, 3, 4, 5 carbons, and that's going to give me the prefix of pent. So we have pent, and then our ending anal, pentanal. And again, when we are looking at this, to name this, we are going to do prefix equals the number of carbons, and our suffix or the ending is always going to be anal. Excellent. Moving on to our next molecule. Again, looking for that functional group, looking for what that could possibly be here. Note that there's that double bonded O as well. And as you look at your reference table, we see that when we have a double bonded O with any sort of carbon chains on the side, that's going to be a ketone. So our functional group here is this double bonded O to our central C. And this is an example of a ketone. Okay, our general formula for the ketone is going to be R-CO-R prime. And again, when I'm looking for how to name these, I'm going to go ahead and take a look at my example. Now note that for ketones, in our example, there's a number that's located on our name. What do you think that number represents? Well, note that I can have any carbon chain that I want on the left and right-hand side of my double bonded O. And so that number right here at the beginning of my name is going to represent the location of my double bonded O. So for this molecule, I have 3 carbons, and so my prefix for 3 is going to be prop. Okay, the ending of ketones is anone. Okay, propanone. Now, I can assign a number to this. Okay, and I will just for the example of naming it. But let's talk about why we might not need a number. So 1, 2, 3. Okay, actually, I'm not even going to assign a number because we technically shouldn't. So we have 1, 2, and 3. Okay, our molecule here, our location is on carbon 2. It's on carbon 2 from either direction that you go, from the left to the right or the right to the left. But here's what I want to point out. What's my major difference here between aldehydes and ketones? They both contain that double bonded O. So what's the major difference between these two? What I want to point out is that for our double bonded ketone, or for a double bonded O in an aldehyde, notice that in my general formula, you're only listed with 1 R group. And that's because aldehydes are located only on terminal carbons. So these are located, okay, only on terminal carbons. Okay, and so my major difference between these 2 molecules is that aldehydes are at terminal carbons and the ketones are only on inner carbons. So for propanone, it wouldn't be considered a ketone if my double bonded O was at position 1 or 3. If my double bonded O was at position 1 or 3, it's no longer a ketone, it's an aldehyde. So the general rule of thumb for ketones, something that I'd like to add here, is that the number is used in the name for chains of 5 or more only. And again, the reason being for that, even with butanone, when we have butanone, we end up having only one position it could really be, position 2, right? Because whether you're numbering from left to right or right to left, it's only going to be at position 2. So we don't need to start using a number for the name until we have chains of 5 or more. So let's go ahead and jot down our general formula for naming ketones. So again, I'm not going to write down the number part, but the number is used to represent the location of that double bond. But our prefix is our number of carbons. Our suffix is going to be a known. Okay, and again, numbers for carbon chains of 5 or more. All right, so last but not least, we end up having an ether. Okay, and so our ether, what's going to be a functional group for an ether? Again, we always want to look for what is not like the other. So we have this single bonded O, and that's going to be our functional group. Okay, and ethers are going to have the general formula, okay, of R-O-R prime, where again, those R's are going to be carbon chains. And when we go to name ethers, what I want to point out here, okay, from your reference table, methyl ethyl ether, okay, methyl ethyl ether is going to be the example that we're provided here. And I actually, I don't really love that example because I actually believe that you're supposed to be naming them in alphabetical order, these branches, instead of reading it from left to right. And so I'm going to stick with alphabetical. So what we need to do is we need to take a look at our 2 carbon branches that are provided here. So in our example, we have a carbon branch here of 1, which is meth. And we have a carbon branch 2, which is here, which is S. And so to name this, again, I'm going to stick with alphabetical order. So we're going to name this ethyl methyl ether. Okay, ethyl methyl ether. All right, now, last thing I want us to do together before we're finished for today is to go ahead and draw and classify these compounds. So seeing if we can go ahead and draw them now from name. So first one that we have here is butyl propyl ether. Classifying this should be pretty easy because guess what? It has the term ether in its name. So our classification here is just ether. When we're drawing ethers, I think it's easiest to go ahead and figure out the number of carbons per each of my carbon chains. So for ether, we are going to have, okay, butyl, which is a 4 carbon, and propyl, which is a 3 carbon. And they are connected by that single bonded O. So we have 1, 2, 3, 4, single bond O, followed by propyl, 1, 2, 3. And from there, drawing the rest of our H's in. Again, filling in so that each carbon has only 4 bonds. And with that double bonded O, remember, oxygen only bonds twice. There are 2 sets of lone pairs there. All right, next, let's go ahead and take a look at our hexanal. That ending anal indicates that this is an aldehyde. Remember, aldehydes mean that our double bonded O has to be on the terminal carbon. So that's going to help us draw this molecule. Okay, hex means 6. So we're going to start by just drawing a 6 carbon chain. 1, 2, 3, 4, 5, 6. Pick a side, whichever side you like to add that double bonded O to. I'm going to add it right here to the front carbon, double bonded O. Again, there are electrons on that O, and now all we need to do is fill in our hydrogens. Now this first carbon already has 3 bonds, so it's going to bond to just 1 hydrogen. Okay, but the remainder of these 1, 2, 1, 2, 1, 2, 1, 2, and 3. All right, lastly, we have our must be a known, but also must be a ketone. And note how we are working in a chain of 7, and because our chain is above 5, we have a location for where our double bond is going to go. So we're going to start with 7 carbons, 1, 2, 3, 4, 5, 6, and 7. And we're going to go ahead and add that double bond to our third carbon. You could go from left to right or right to left, whichever floats your boat. I'm going to go ahead and just go left to right, so our double bonded O located on carbon 3. And again, now all we have to do is fill in hydrogens. 1, 2, 3, 1, 2, 1, 1, 2, 1, 2, 1, 2, 1, 2, and 3. All right, everybody, that's ethers, aldehydes, and ketones. I will see you guys tomorrow for some practice. Have a great rest of your day.